Welcome to this discussion of the first part of Section 2.3. Section 2.3 discusses divisors and greatest common divisors among the integers. We'll study both properties, definitions, as well as theorems concerning greatest common divisors in this section. In Section 2.4, we'll find an efficient way called the Euclidean algorithm for finding greatest common divisors. Let's begin with the definition of being a divisor. We say that integer a divides integer b if there is a third integer c such that a times c equals b. I want to pause for just a moment here and just point out that we've reversed the roles of a and b in this from that used in the division algorithm. It doesn't really matter what roles they fulfill. It just might be slightly confusing that we have switched them. Remember, the way we typically wrote the division algorithm was that we said that given a and b, where b was not 0, we had a equals b times some quotient plus a remainder, where the remainder was greater than or equal to 0 and less than b. The problem with this is that we've interchanged the roles now. Instead of having b be the divisor, as we did in the division algorithm, now a is the divisor. It's the number we're saying divides the other one. So throughout this section, whenever we choose to use a and b, we'll traditionally, in this section, think of a as the divisor and b as what I'm calling the dividend, just to encourage you to be more flexible. So continuing on, we say this relationship in several different ways. We say, for instance, a divides b, or b is divisible by a, or a is a factor of b, or b is a multiple of a. In any case, we write a and then that vertical line, b. I just want to mention that when you're in an area of mathematics and you find there are 4 or 5 different ways to either say or annotate some fact, it means that particular fact or idea or relationship comes up frequently. And the idea of dividing something is really central in number theory. I also want to mention that if a divides b, then of course minus a divides b also. That is, divisors occur in pairs. The negative of any divisor is another divisor. For that reason, we'll generally concentrate on the positive divisors and often not even list the negative ones. But that doesn't hide the fact that the negative ones are also divisors. For example, minus 15 is divisible by 1, by 3, by 5, and also by 15. I didn't write down the fact that, of course, minus 15 is divisible by minus 1, minus 3, minus 5, and also by minus 15. And then we start on an important theorem, number 2.2, which lists some of the very basic properties of divisors. And I'll quickly read over them. Some of them are pretty obvious and you know them. Every number divides 0. 1 divides any number. Every number divides itself. The only thing that divides 1 is either plus 1 or minus 1. And in part C, we mentioned the fact that if you have a dividing b and c dividing d, you can basically multiply the two sides of that almost as if those are equations. That is, a times c divides b times d. And then part D of this theorem, if a divides b and b divides c, then a divides c. Think of that as what we call a transitive property. This is a chain, C-H-A-I-N, a chain, and you can have longer chains once you know this fact. That is, if a divides b, and b divides c, and c divides d, and d divides e, then of course a divides e, by applying this over and over again. We're going to go through a proof of part D. It's typical of the proofs of the rest of these. The textbook actually skips the proofs of all of them except the last 2, and leaves them for you to sort out. I'm going to go through D and give you an idea of how these proofs are done. So, for example, for part D, what we want to do is assume that a divides b and b divides c. Remember, this is the transitive property one. So, if we assume that a divides b, then we know there's a number n such that a times n equals b. If we assume that b divides c, then we know there's an integer m with b times m equals c. So the idea is we can substitute the product a times n, which is b secretly, for the b in the second equation. So we get a times nm equals c, rewriting that second equation. So now we have a number, nm, that multiplies a to give us c. So that means that a divides c. This is generally how one goes about doing all of these proofs. They all deal with assume this, that, and another thing, and prove that one thing divides another. A divisor divides a dividend. To do the proof, you almost always construct a multiplier. Construct a number, just as we did here, the number n times m, that you can multiply by the divisor and get the dividend. And you come up with that using the assumptions. That's the general approach to all these proofs. Let's talk about f. This is actually in the textbook, but he assumes a couple things that I want to point out, and then I'll go through the proof. He assumes you know, first of all, number one, if you have two integers, x and y, then the absolute value of the product, xy, equals the absolute value of x times the absolute value of y. You can verify that just looking at the different cases of the different signs of x and y and using our definition of absolute value. Secondly, he assumes you know that if x is greater than y, and you multiply both sides by a positive number, and call it z, then you get another true inequality with the sense, the direction of the inequality, the same. That is, if we have x is greater than equal to y, and z some positive number, then xz is greater than or equal to yz. You do know, by the way, there's another case of this that we're not using in this theorem, so I didn't write it here. But of course it is important and comes up, and that is if x is greater than or equal to if x is greater than or equal to y, and you have a multiplier that's negative, you'll get another true inequality involving the xz and yz, but the sense reverses. That is, if x is greater than or equal to y, and z is less than 0, then xz would be less than or equal to yz. We're not using that in this, so I didn't write it down. So anyway, now we're ready to talk about the proof of part F of Theorem 2.2. And the idea is that, again, we want to figure out what our assumption tells us. So we assume that A divides B, and that B is not 0. So we know there must be an integer C such that A times C equals B. And in this case, we know C cannot be 0. And the reason C can't be 0 is because B isn't 0. That is, if C were 0, then A times C would be 0. And since A times C equals B, that can't be. So C is not 0. So C is an integer which is not 0. So we can write just to the right then that the absolute value of C must be greater than or equal to 1. And now what we're going to do is multiply both sides of that inequality by something that we know to be positive, namely the absolute value of A. So in the next line we get that absolute value of A on the left, that's 1 times the absolute value of A, is less than or equal to, on the right, absolute value of A times absolute value of C. Again, that was by multiplying both sides of the above inequality by absolute value of A. Of course, the absolute value of A times the absolute value of C is equal to the absolute value of A times C, which is equal to the absolute value of B, since AC equals B. So in this inequality, we have on the far left absolute value of A less than or equal to, and on the far right absolute value of B, which is what we wanted to prove. That's about the only one of these that's not of the nature of showing something divides something else. If you do G, you're back to that, coming up with showing that something divides something else. See if you can do G on your own. Construct the actual multiplier using the assumptions. If you get stuck, check the book.